All right, let's look at some more constants, right? This is the permittivity of free space. You will use that probably almost never, right? Okay, let's see. Capacitance. Capacitance is epsilon naught area over d for an air gap capacitor. So that's free space. If you fill that with plastic, well, plastic will have a higher permittivity. Okay. Um, Honestly, I just looked through the data packet. I can't find where they've used that. This is the permeability of free space. This is the magnetic thing, right? And so if we take the integral of what of the b times the distance or something like that, right? Around there, it will equal. This is Ampere's law, right? Mu naught times I, right? So this ends up being 2 pi r times the magnetic field is mu naught I. Okay. Well, one last thing. This is the constant for electricity. This is the constant for magnetism. Okay. This is capacitance, right? But the speed of light, little c, is actually 1 over the square root of epsilon naught mu naught. Okay. That's one interesting thing. So just try that. You put those numbers in, right? The second thing is, what the heck kind of constant is 4 pi, right? It turns out it was close to 4 pi, right? And so they just made it 4 pi because that's very handy, and there it is, right? Okay, this is exactly what it says, speed of light in a vacuum. It's 2.998 if you've got 4 sig figs. But anyway, times 10 to the 8th. That's the fastest speed there is. Planck's constant you'll use. So you'll use speed of light in a vacuum. What is it? Velocity is frequency times wavelength. So for an electromagnetic wave, the speed is, of course, the speed of light, right? So you plug it in there. It's also you also use it in E equals mc squared. So if you're converting mass to energy, right, you'll use it for that. Use the speed of light for finding the energy of something, right? Because the energy is hf, which is hc over lambda, right? Anyway, there it is. This is the elementary charge. So this is the charge on an electron or a proton. Notice they give it to you as a positive number. An electron has a charge of negative 1.602 times 10 to the minus 19th coulombs, right? And a proton would be positive that. Mass of an electron, of a proton, of a neutron, right? And just be careful. Don't use this guy for binding energy, I'm just going to say. But there, notice that electrons are much less massive than these guys. Notice that a neutron's more massive than a proton. And then this is fun. We'll use this all the time, right? So unified mass unit, which is 1/12 of carbon 12. Okay, literally that's what a U is, right? Is this many kilograms? And we hardly ever use that, but sometimes we do, right? And then if you want to turn it into energy, that is, if you have a mass defect, a nuclear reaction, right? It's left side minus right side times 931.5. In nuclear, in a nuclear problem, if you're in doubt, just do that, right? Solar constant, that's fun. This is 1360 watts per square meter. My sister is a solar engineer, so she'll look outside on a day and she'll go, oh my gosh, she says it's got to be 200 watts per square meter, right? Okay, so this is a bright sunny day in the summer. This is what we get at the surface of the Earth, I think, or maybe I think that's the surface of the upper atmosphere, right? It is not constant. When there's sunspots, the sun is brighter, et cetera, et cetera. And then this is the Fermi radius. So this goes. The radius is this guy, and then a to the 1/3. It's use that in there. So it's the Fermi radius. All right. Oop, obviously, I've got to go here.